Hi, everyone. Hopefully you're here to hear about Ethernet, because if you stay in this room, you will anyway. I'm Nate Graff. I am the retiring Hardware Outreach Officer. It's been an absolute pleasure being Hardware Outreach Officer for the past 2 years. I am also hopefully successfully defending my master's thesis this quarter whenever I manage to schedule that. I have 4 weeks. So, jumping into it, the OSI model, because you have to start somewhere. The OSI model breaks up the network into layers. And so the physical layer is layer 1, then you get the data link layer, and then the network layer, and then a bunch of other stuff we don't care about. But most important for this talk is that Ethernet defines these two, the physical layer and the data link layer. So what physically is transmitting information from point to point, and then how we coordinate and describe the information we're sending through that physical medium. There are a number of major concerns of Ethernet, and these will be like segments of the talk. The first is, what kind of wire are we using to actually send information from place to place? Second is, how do we encode symbols onto this wire so that we know what language we're speaking and what actually means anything on a piece of metal? Then there's, how do we coordinate sending and receiving symbols along the wire? So obviously we have to be on the same page when we're talking to each other. How do we organize symbols into things that are more than just a 1 or a 2? So how do we actually encode larger chunks of information? And then how do we provide an interface to the network layer, layer 3, so that we can have the rest of the network on top of it? Because obviously Ethernet is one medium. We also might have Wi-Fi, and they both have the network layer on top of them, and we just swap them out from underneath. So first, what kind of wire are we using? Does it matter? Yeah, it does. But why does it matter? It matters because the kind of wire we use determines how far we can send a signal. And that's because wire has resistance to it unless it's some sort of superconductor. And the further we go, the more that resistance degrades the signal we might have. The more that wire acts like an antenna to pick up signals we don't mean to have. How fast do we want to send information along the wire? The design of the physical piece of metal we have determines how quickly we can send signals across it, because the faster you want a signal, the more you have to design the wire to be able to propagate signals at that speed. Under what conditions do we want this wire to work? Do we want it to work in outer space where there's no magnetic sphere of the planet? Do we want it to work underwater? Do we want it to work in what kind of radio environment? All sorts of stuff that we need to take into account when we're designing the wire. How much is it going to cost to make this wire and install it? Because even if you make the perfect wire, like I said, superconductors, who can afford that? Especially when you need to run it the entire length of a building sometimes. And finally, how reliably do we want to be able to transmit information over this wire? Because the more reliable it needs to be, the more we need to be able to shield the wire that's actually containing the information from spurious transmissions, which means we have to add more metal to the wire and all sorts of other stuff, which increased costs and change how far things go and all sorts of stuff. All of these things are pretty much interrelated, and why I'm not a mechanical engineer. What do we mean when we say Ethernet? A whole lot of stuff. This is a table off of Wikipedia. I think that's the entire table. And it has 65 different entries describing 65 different standards published by IEEE for the 802.3 specification. And each of these might contain various substandards. So you have like some signaling protocol on top of different media and all sorts of stuff. One of the documents I downloaded was 802.3-2015, which is presumably a standard made in 2015. Anyone want to guess how many pages that document had? 2,000 is close. It's actually double that. It was 4,017. And that only went through 10 base whatever, which was like the 90s, maybe the 80s, something like that. I don't care. So the designations for Ethernet look something like this. In this case, we have 100 base T. The different parts of this designation mean different things. So the 100 is the rate. base means how we're remodulating it, and T is the medium. So in this case, we're sending data at 100 megabits. We're modulating it in the baseband, meaning we don't have it up at some high frequency like we do for radio, where we have to make it to like 90 megahertz or whatever. Baseband means the signals of the actual data are in like go down to 0 hertz, though they don't actually in this case. It's just baseband, meaning we're not modulating the signal we want to transmit up to a higher thing like you do in cable or radio. And finally, the medium. In this case, T stands for twisted pair, which is the kind of Ethernet cable we're all used to looking at. But there are other types of Ethernet cables. The first being coax. Believe it or not, coax, like you get for your cable provider or something, was the first cable that the people actually made Ethernet with. So I think 10 base 10 base 5 or whatever is like over coax or something. Twisted pair is, of course, Ethernet. We're using the same picture from the title slide for efficiency. And then, of course, if you want to get faster than copper can transmit stuff, you get into optical fiber, where you're using actual light bouncing around inside of a piece of plastic to get from place to place. So twisted pair is what we're going to talk about here, because I didn't have time to learn how fiber worked, and no one wants to hear about coax. So twisted pair wires for Ethernet have 4 pairs of differential signal lines. So 4 pairs of wires, each pair has 2 wires in it, and independently transmits signals along it. The pairs are usually color-coded: red, green, blue, and orange. And those are important for people who actually care. No, those are important for distinguishing which pair is going on. And there are various categories of twisted pair cable. You typically hear of them as like Cat5, Cat5e, Cat6. The higher number means that it's like a later iteration that has more strict requirements for what kinds of signals can be propagated for how long, how quickly. The iteration was to support features of the evolving standards. So the manufacturing techniques available when twisted pair was first introduced weren't necessarily quite there, or even the data processing techniques weren't there to handle higher signaling rates. So they just made it good enough for what they needed. And then later, when we had gigabit Ethernet, they were like, oh, well, we need better cables. And so that's the higher categories. And then finally, we terminate the twisted pair in an RJ45 connector, which is the standard Ethernet connector you're used to seeing. It has 8 points for all 4 pairs that are on the twisted cable. So what do I mean when I say differential signaling? So the 4 differential pairs transmit signal between the 2 of them, instead of the normal thing where you have a ground wire and a wire that's above it that turns on and off. And we do this because it has high common mode rejection. Don't worry, I'll get into what that is. But basically, if you have the difference in voltage between the 2 wires instead of the voltage on one wire, you can input a signal and have the difference come out the other end. But if noise gets put on both wires at the same time, it doesn't change the value of the output at all. So getting into differential mode, I'm kidding, I'm not going to talk about that. So we have 2 wires. And we're going to look at the voltage over time as we get some spurious radiation coming in on them. The last slide is important, but it's not important here. So it's a really cool thing. If you get into any of the 300 level EE courses, those are really neat. But so we have an incoming wave, and it causes the voltage to go up on both wires at the same time. And the whole point being, if you take the difference in voltage between the 2 wires at any point along there, it's negligible. You might have some different time. You might have one wire have a slightly more voltage on it, but the common mode gain is small. It rejects common changes in both wires. Since we only care about the difference, if they both change about the same amount, then the voltage difference doesn't change. And you can transmit signals without as much or any shielding for longer distances than you can if you have a single signaling wire and a ground wire. So if you notice, Ethernet doesn't have ground. It only cares about the voltage between the two wires. The voltage is referenced between either of them. So we have an ability to send signals along a certain piece of metal. That's part of the PHY layer, but we also care about how we actually put voltages deliberately on that wire. And that gets us to symbol encoding. And this changes a lot depending on what wires we're doing and what modulation schemes for what generation and speed. So we need to define what standard we're talking about. In this case, we're going to talk about 1000 base T or plain old simple gigabit Ethernet, which is what we pretty much need to worry about in any given moment anyway. How do we encode symbols on this wire? We do something called Pulse-Amplitude Modulation. This is a generic example of Pulse-Amplitude Modulation. What you essentially have is the sinusoid, in this case, is the information we're trying to transmit. And then the carrier is not like some really fast signal like we do in AM radio, where the carrier is in the kilohertz, something like that. I don't know, I'm not into radio. And it's something that's also at a low frequency. And when you modulate the two, meaning multiply those two signals together, you get the bottom trace, which is a bunch of pulses that outline the signal we're actually trying to carry. So in gigabit Ethernet, the kind of pulse amplitude modulation we do is called PAM5. And we call it that because there are 5 discrete voltage levels of the actual signal. And every pulse takes on one of those 5 values. So it looks a bit like that. You have 5 distinct levels, and the trace goes between each of those levels in turn. The signaling rate, meaning the rate at which you change voltage levels, is only 125 megahertz. And this is in gigabit Ethernet. So how do we actually get a billion bits per second along this wire? Well, we remember each of these symbols encodes 2 bits of information. And that's 2 bits because it's 5 voltage levels, but we actually move between all 5 in a certain way in order to encode only 2 bits of information per 5 discrete value signal. And then we also have 4 differential pair lines, each of which can have a single symbol on it. Which means when you multiply all this together, you get 4 lines at 2 bits per symbol at 125 symbols per second, which multiplies out to a billion bits per second. So how do we get from 2 bits to the 5 symbols? We use something called Trellis-coded modulation. And this is what converts the bit stream into symbols. What it does is it takes 2 bits as input and outputs a 5-bit or a 5-level signal. And what this does is it provides error correction and increased throughput along the wire. How it works, I don't know. It was too complicated for me to learn today. So this is what I got. Next up, though, how do we coordinate sending symbols between? Oh, first off, do we have any questions so far? At least questions I can answer, because I don't know how Trellis-coded modulation works.
Wait, so does that coded modulation thing, is that about the changes between the most recent symbol, the most recent voltage and the current voltage?
Yeah, it's some state machine.
Okay, cool.
So depending on which 2-bit symbol, sorry.
So it takes the 2 bits and the previous voltage?
There's some state machine in there. It might. I think it could very well be just the most recent symbol output, but it could also be some arbitrary set of states going into the past arbitrarily long. A simple example is the most recent state it was in, then determines what state it goes to next. And again, that. Anyway, so any other questions? So we got our physical media. We got a way of encoding some amount of information onto the wire at the data rate we want. How do we actually coordinate when people send symbols to each other? Well, early on, we had to do something called collision sensing, because old Ethernet had to share time on the wire. Each side of the wire had to say, OK, I can send something now. I can't send something now. And the way that generally worked was, if no one's sending on the wire, start to send a message. If you accidentally stepped on the other person's toes, then back off, wait for them to send the message, repeat, do all sorts of stuff. This kind of sucks. So what we do now is called Full-Duplex, where you can send and receive simultaneously on the same wire pair. It's actually really neat. But how can this possibly work? Something called superposition. And so to demonstrate that, we have a Slinky. The Slinky here is attached on one end, and someone is shaking it on the other. And so they send a wave into the wire. And what it's going to do then is bounce back. But for some extent here, you can actually imagine that someone's shaking on the other end. And so the two waves can just go right past each other because they don't really care that there's a wave on the wire right now. They're in superposition when they overlap. And so you can see there's some reflection when it goes off the side that's connected to the wall. The way Full-Duplex has to work is it has to know what symbols it sent on the wire and then wait for reflections to come back and know that that's not the signal its port partner sent. So it sends symbols on the wire, it knows what reflections are going to come back, and when it receives something that isn't a reflection, it assumes that that's an actual input to the wire. Full-Duplex is a bit easier on a physical wire than it is on a radio system where you have an antenna and all sorts of fun stuff that's involved with that. Whoop. How did I? There we go. Apparently there's a button that swaps screens on this. I did not know that. So we have a way to coordinate symbols. We don't have to. How do we organize symbols into meaningful amounts of data that we actually care to receive or send? So we want to get to the ability to send frames to each other because the data link layer would be nice if we could actually send a chunk of data to the port partner and actually have them receive something that's usable. So we'd like to send a chunk of data. And layer 3 would really like it if we could send a packet. Because layer 3 is the network. They want to send data between hosts on a whole network of Ethernet stuff. So it'd be really nice if our chunk of data we sent had the network layer encapsulated in it. And the data we send has to have some metadata describing it, things like the source of the data, the destination of the data, and some kind of checksum so that we know that our data got sent along the wire properly. But there are a number of problems with actually ensuring that, all having to do with how do we actually get these chunks along the wire? Because we need to do things like know that the wire is plugged in. We need to be able to synchronize across the channel so that we know when the pulse is actually the pulse we're trying to look at and not some kind of edge between pulses or something like that. And we need to know which pulses are the packet and which are spurious or sent at the wrong time or anything that could be an error instead of the actual packet we're trying to receive. And so Ethernet has a specification called the physical coding sublayer that describes how we solve all these problems. So layer 1 has its own kind of packet. And what the layer 1 physical coding sublayer says is in a packet is a preamble and frame delimiter. And so this is how we actually notify the receiver that it's going to have to pay attention to what's coming next. Then we have the layer 2 frame that's right after the preamble and frame delimiter so that we have something actually being sent. We're not just saying, hey, wake up. Hey, wake up. We're actually saying something. And that has the data and the metadata about the packet. And then we have an interpacket gap, which is the minimum interpacket spacing so that we don't overwhelm the receiver with stuff. It has time to actually do what it needs to do. So the preamble and delimiter is 7 bytes of alternating ones and zeros. It's pretty common for a preamble on a layer 1 system. And then 1 byte of a different value. And it's really the way to say ready, set, go to the receiver on the other side of the wire. It looks like this. And you note that the different value is just the same ones and zeros with a 1 at the end. That's really useful, though, because it means that at any time along this bit stream, you can jump in. So if you miss the first byte, 2 bytes, it doesn't matter. All you're doing is trying to synchronize to that clock on the wire. And then all of a sudden, you get this 1, and you're like, oh, shoot, the very next bit is the first bit of the actual packet we're trying to receive. Any questions on that? Or anything else I've gone over so far? Yes?
So will that always happen in a case like this where the last bit will be a 1, or would it also be a case where you'd have 2 zeros in a row?
That would also be possible.
Okay.
It also depends on the actual specification of how you encode the stuff onto the PHY. In this case, this is how Ethernet does it.
Why do we need that inter-packet gap? Like, what takes the time between packets?
So if the receiver is doing all of, so when this data is coming in on the wire, you have delays due to, like, the receiver has to filter out noise, has to actually do the difference between the voltage lines, has to pass that data onto some kind of latching mechanism, and then probably some sort of digital processing mechanism has to notice that something's happened and actually gather up all the bits and pass them on to the next subsystem. And any number of those things can have some amount of latency. So they added a gap, probably based on some kind of empirical measurement about how long that stuff takes, to make sure that a given implementation can be built and can be built for not too much money. Cool. So again, the interpacket gap is a minimum of 12 bytes of silence. So that's actually not much space at all. The preamble was 8 bytes, the preamble and delimiter. And you get up to like 1,500 bytes of actual stuff in the packet. So 12 bytes of silence is very little time compared to how long the packet can be to begin with. So it's really conservative in terms of how much time it actually provides the receiver to catch up, or mustard. Really dumb joke. Yes.
So by 12 bytes of silence, you mean for the amount of time it would take to transmit 12 bytes, you transmit nothing?
Mm-hmm.
So you don't transmit zeros, you actually just don't transmit anything?
That's a good question. That detail eludes me.
You kind of know, because it's 96 bits at a billion bits per second. So you just kind of chill for whatever that ratio is. So,
Yeah. We're talking real short.
96 over a bit.
Oh, wait, no. Yes, 96 bits at a billion bits per second. And again, it gives the receiver time to send the frame to the layer 2 processor, do whatever filtering it needs to do. It's just enough time so that you don't saturate the processing too badly. Though obviously you could end up dropping a packet if you got overwhelmed. And so the layer 2 frames are what we encapsulate in this layer 1 packet that we send along the wire. And that has the destination MAC address, the source MAC address, an identifier called the Ethertype, which describes the type of payload we're actually transmitting, and then a cyclic redundancy check, which determines that the packet actually got sent properly along the wire. So MAC address. What's a MAC address? It uniquely identifies a host on a local area network. The fact that it's not necessarily unique doesn't really matter here. We just assume it's unique for all intents and purposes. And it's a 6-byte value that is associated with your computer. All of you are probably familiar if you looked at the settings for your network on your computer. You have some MAC address. And then there's a couple special ones. The most important is a broadcast address, which in this case is all ones. And broadcast just means it gets sent everywhere on the Ethernet network. So what does this network look like? Looks like this. The unicorn stands for the magic on the other side of the modem. And so it's some combination of routers, switches, hubs, and hosts, which forms a tree, so that the hosts all communicate up the tree and then back down to the other hosts on the network. And each wire between a host and a switch and a switch and a switch and all sorts of stuff is an individual Ethernet cable. Though actually prior to certain Ethernet standards, because the Ethernet cable only had 2 of the pairs used at a given time. So there was actually an opportunity to share a single cable for multiple users. That was fun. Turns out we need better throughput instead of more hosts on a single wire. Each device on the network gets a MAC, and packets get forwarded through the tree until they reach the destination MAC. And so if we have our topology, we have a packet. If host A wants to send a packet to host B and it knows it's MAC, it just gets forwarded along the network until it gets to MAC B. And the Ethernet layer handles sending data between MACs and whoever else. Yeah. So we have an ability to send packets along a network. Now we need to actually interface the next layer up. And we do that with the Ethertype packet identifier. So the Ethertype defines what the encapsulated protocol is. And examples of this are IPv4, IPv6, the address resolution protocol, Wake on LAN, and a bunch of other this ruined the timing of the joke. And a bunch of other junk I've never heard of. You can go look at the list. There's a bunch of junk in there. Who knows what it's for? But the address resolution protocol is really what we want to talk about here, because it's the bridge between layers, the network layer and the layer 2 data link layer that we're currently at. And what it does is it says, OK, well, I'm trying to get a packet to this IP address. I don't know what the Ethernet doesn't know what an IP address is. So what the address resolution protocol does is it gives you the ability to ask the question, which MAC has this IP address? And so you can say, who has IP 192.168.13.37? And then the host that ostensibly has that IP, though it may not, if it's lying, will say, I do, and this is my MAC. And then the host can do what it did before and send a packet to that MAC address. And we have successfully bridged to layer 3 of the network layer. And that's all I got, so I can answer questions now.